Right, we're going to do our examination review, or a review of analysis of beams in Flexure. And this will cover over what we have done so far this semester. Work a couple of examples. So we're going to analyze a beam in Flexure. So Flexure again, just to make sure that we all remember, is where the loading is occurring along the length of the beam. It may be a very large load, say 250 kips, and or a distributed load, say that's 50 kips per foot. Here we have our span length, capital L, and this, of course, as you know, will cause a bending moment to occur within the slab. Within the beam. Slabs are beams as well, but occurs within the slab. In order to resist that, we are going to use, and this is our section, steel in the tension zone. We're going to use concrete in compression. And we're going to have a strain distribution that looks like this. This is our depth of the neutral axis, C. And we want to be in tension control, or ultimate limit state. Tension means that the beam fails by stretching steel. And that is an advantage because it warns us it's coming. We do not want to fail in compression where the concrete would crush, so that's not an acceptable and ultimate limit state. And so what we have under these conditions is, so long as the strain in the steel is greater than 0.005 when the concrete crushes, which is a concrete strain of 0.003, then we are in tension control. Tension control, our phi factor is equal to 0.9. We're very happy about that. We defined the term rho, the reinforcement ratio, which is AS over BD. And so long as rho is greater than rho min, and rho is less than rho max, then we are in tension control. Our rho min, rho max measurements, rho min is equal to either 200 divided by F sub y, or 3 times the square root of the compressive strength over F sub y, whichever is larger. And our rho max for 4 kips per square inch concrete, and F prime y is equal to 60 kips per square inch, is 0.01806. And that's true because it's dependent only on the reinforcement ratio. And so we use this method of our reinforcement ratio to perform our analysis. How do we do that? We also use our friend Whitney. The Whitney stress block says that A is equal to beta 1 times C, and that if this is true, that the compressive force in the concrete is equal to 0.85 F prime CAB. The tension force in the steel is equal to AS F sub y. F sub y because it's yielding. If we take from statics that the forces are in equilibrium, then we know that our tension force in the steel is equal to our compression force in the concrete. We can solve that A is equal to AS F sub y divided by 0.85 F prime C. B, rho is equal to AS over BD. If rho is less than rho min, then that is a failed beam. It's inadequate. If rho is greater than rho max, it's a failed beam. It's inadequate. If rho sits between rho min and rho max, then it's in tension control. Phi is equal to 0.9, and our nominal moment is going to be equal to ASFY d minus A over 2. And our design moment or ultimate moment is phi m sub n. So that's what we do with tension reinforcement. It's either going to be under reinforced, over reinforced, or it will be in tension control. If it's in over reinforced or under reinforced, then it's inadequate. Otherwise, we use this equation to compute our example. So let's do an example. We'll start on a new piece of paper. We'll do an example. We have a beam. It has a cross-sectional area. Width is 8 inches. Depth is 18 inches. It's reinforced with 3 number 8 bars. F prime C is 4 kips per square inch. F sub Y is 60 kips per square inch for the steel. The cover is equal to 2 inches. So how do we use this, these things we've been talking about to do the analysis? Step 1, we check rho. Rho is equal to AS over BD. AS is equal to 3 multiplied by the square by the area of a number 8 bar, which is 0.79. B is equal to 8 inches. D is equal to 16 inches, which is the depth of the beam minus the cover. This is equal to 2.35 square inches. And rho is equal to 2.35 divided by 8 multiplied by 16. That is equal to 0.01857. Rho is greater than rho min, which in this case is 200 divided by 60,000, which is 0.0033. Rho is less than rho max, because rho max is equal to 0.01806. Beam fails, is inadequate. Let's take a look at a different beam. In this particular case, let's have a beam still 8 inches, 18 inches. Cover is 2 inches. F prime C is 4 kips per square inch. F sub Y is 60 kips per square inch. This time we'll go with 3 number 6s. Collect our terms. A sub S is equal to 3 times the cross-sectional area of a number 6 bar, which is 0.44, which is equal to 1.32 square inches.